Welcome back, my friends and fellow jet spacers. Today we're going to talk about moving beyond the idea of a fixed origin in a vector space, and in fact, we're going to privilege the zero vector a lot less. This will be done with structures of, affine, projective, and G structures. Okay. Now, we're going to first use the idea of an affine space and barycentric coordinates to handle combinations of points without relying on some fixed origin. We're also going to talk about projective spaces by homogeneous coordinates and study the invariance across them, like the cross ratio. We'll also reduce the linear frame bundle to G structures, or just subgroups, G being a subgroup of all the set of matrices that are possible, pretty much. And this will be important for metric and symplectic forms. And this is going to encode geometric data, but we still consider this linear. You're just kind of handing the baton off to differential geometry and differential topology. But this is still linear because we're staying within the affine space, and we're going to recover levi-civita connections to induce connections for transport. For parallel transport. So you can think of levi-civita connection on the Riemannian metric, just as metricity plus zero torsion. This will help us measure intrinsic curvature by Cartan equations or the Riemann tensors. Right. So the vector spaces, again, privilege zero, the zero vector, and many configurations like center of mass or position coordinates are invariant under translation. So we can take advantage of this invariance or this symmetry. So the projective geometry will add points at infinity, so that parallel lines will meet, and on manifolds, they become. Sorry, hold on. My thing is tweaking out. I don't feel like you're starting the video. But anyways, so where was I? Oh yeah, on manifolds, tangent spaces at different points must be compared with connections and curvature quantities, and these will quantify the obstruction to the existence of a flat affine coordinate globally. And we can just think of this chapter or this episode as just like connecting the classical affine projective ideas to bundle theoretic tools. Now, let's talk about an affine space. So an affine space consists of a set A and a vector space B. That's it. And a vector space is just going to be this. We're just going to try to have a faithful transitive action acting on some P and V elements of these two to just be P plus V and satisfy associativity. Now, such that for any P and Q in A, there should exist a unique vector Q minus P. And this is what we call, really, this is a better way to view it, because what this will allow us to do is define a normalization condition for how we choose to weight all of these P vectors, right? And they're precisely defined when the lambda sub I are normalized, and this is independent of any auxiliary choice of origin. So, for example, the barycentric coordinates. Let's just say we have a triangle, point A, point B, and point C, and then any point x, y in the affine space will emit some unique set of lambdas such that they're normalized. And this is kind of like a generalization of convexity, but explicitly we can have x and y and lambda sub a being just this nice parameterization. And what this will allow us to do is calculate the centroid with all weights being 1/3. And in general, lambda equals the ratio of the opposite subcomplex volume, subsimplex volume to the total volume. And simplexes are just these are these generalizations of triangles, but just the simplest way to connect them. All right, now simplices. Now, projective spaces. A projective space P of V is a set of one-dimensional linear subspaces through. Basically, they're just lines through the origin. They're lines through zero of the vector space that we're interested in. So that's what a projective space is. And homogeneous coordinates, we'll say a point of on the projective space in dimensions is the equivalence class, since that lambda is not equal to 0, but that they all pass through the origin. An affine charge will arise where x sub 0 is not equal to 0 by this ratio. Okay. Now on the cross ratio on the projective on the real projective line in one dimension, this will be an affine coordinate t at t of x x sub 1 over x sub 0 away from the poles of this. And these projective transformations will act like these fractional linear, or in other words, Mobius maps, where we have t mapping to pt plus q over rt plus s. And substituting shows that the cross ratio is unchanged, and it will be the fundamental invariant of 4 collinear points under the projective group. Okay? And what this will allow us to do then is motivate the idea of frames, G-structures, and connections. Because at a point on a manifold, we can define something called the frame of P on M, which is just the space of ordered bases of the tangent space. And their disjoint union with the topology essentially encodes something called the frame bundle. If we just do all of their disjoint unions, the frame bundle of the manifold is a principal GL bundle. Okay, and this will just be a general linear bundle in dimensions over the real parameterization, or not parameterization, over the real object that is encoding, or that's the ordered basis of the tangent space. Sorry, I'm like tripping. But it's the GL bundle. Okay, and we can generalize this. A G structure is a smooth reduction of the structure group, essentially to a subgroup of G, which is a subgroup of the general linear bundle. So we can have a G structure that's just a space of orthonormal frames. We can have this if and only if there is a Riemannian metric, or if we have the G bundle of these symplectic frames, we can have this if and only if we have a degenerate 2 form on the tangent space. And a connection then is said to equip the bundle with a G equivariant horizontal distribution, defining the parallel transportive frames and technically tensors along curves in the manifold. Now, what this allows us to do is say, well, we can describe Cartan structure equations. I missed it. But we can say omega, let this be the connection 1 form, which is Lie algebra valued, and the theta, or tautological / solder form, the structure will read as the exterior derivative acting on the Lie algebra valued connection 1 form, which gives us, omega, capital Omega, wedge omega plus torsion, or theta. And this other structure, which is the exterior derivative of this omega, should be minus omega, wedge omega plus phi, which encodes the Riemann curvature tensor. And this is nice because what this will allow us to do is both encode the Riemann curvature tensor and the levi-civita connection. And what this looks like then is, given a Riemannian metric, let's say G sub ij, the unique connection satisfies 2 things: metric compatibility and torsion free. So we find a symmetrization of the Christoffel symbols under both of these indices, as well as the covariant derivative. Basically, this covariance basically its connection is unique because the covariant derivative of the metric is equivalent to 0. That makes sense, right? Now, the Christoffel symbols then can be made out of this cyclic permutation of metric compatibility identities, which will yield the nice classical formula for the Christoffel symbols and all the curvature and everything. So this should be an exercise that you derive. Okay, and the Christoffel symbols define the unique levi-civita connection. Now, we can look at flat polar coordinates where we puncture and create that point at infinity, and or I guess point at 0 technically. But for non-vanishing symbols, because of the way that the indices are symmetric, we can have 1 over r, and the gamma for the theta indices are minus r. And if we were to substitute this into the general Riemann formula, this would give us a Vanning curvature tensor, and this punctured plane becomes flat. It's kind of like if you had a flat plane and you wanted to curve all of it into a sphere, that's what it would look like, and extend smoothly through at the origin in Cartesian coordinates. Okay, so that's like how we understand the divergence at the origin. Okay, now a round metric. So say we have a round metric on the 2-sphere, then we can have some key derivations or key symbols, which is the negative of sine of cosine and cotangent. And what that allows us to do is then encode Gauss curvature first, or the scalar curvature would be 2 for the unit sphere. So everywhere r is equal to 2 as a scalar curvature, and the Gauss curvature is 1. Curvature 2 forms and Riemannian components are non-zero, but they distinguish the sphere from the flat plane, and that's essentially everything that we're doing with our Lorentz invariant quantity. Okay, now how to fit the pieces together. The affine geometry will allow us to essentially we get rid of the privileged origins with vector spaces by defining the pair of an affine set and the vector space. The barycentric weights will give intrinsic convex combinations, and homogeneous coordinates will turn to projective geometries into linear algebra, and the cross ratio will survive all of the projective symmetries. Frame bundles organize bases, g-reductions impose geometric structures like lengths and angles onto symplectic forms, and connections enable consistent differentiation and parallel transport. And finally, the levi-civita connection is the unique torsion-free metric-compatible connection, and the curvature measures deviation from flat affine charts. Now, how we want to think about all this is just affine spaces. They're the difference of vectors. Differences are vectors, and combinations require weights summing to 1 for preserving the barycentric relations. We also need to make sure that the projective spaces, like lines through an origin or homogeneous coordinates, they're cross ratio and invariant. They're key invariant. For example, something such as the Mobius transformations. Okay, and finally, G structures and Christoffel connections and connections and Levi-Civita connections. Basically, we're parallel transporting by Christoffel symbols from metricity. We are reducing frame bundles to preferred frames to encode the extra structure. And metricity, zero torsion. This curvature then gives us Riemann tensor and Cartan forms to detect intrinsic geometry. Think about like a flat plane versus a round sphere. All right. So here's a couple questions that you probably would want to be able to answer to make sure that you learned anything from this episode. And here's some problems that you can practice. And here are some mastery problems if you want to become one of the best in the world at this stuff. All right. Thank you for watching.